Hey, James, sorry, just want to step in. Could you unmute real quick? No problem.
My bad. I was waiting. I was trying to have the screen open and was waiting for the music. So my bad. Welcome everyone to um, office hours for the persistence of memory sprint for Topl. Um, I'm James. I'm the CTO and one of the co-founders over at Topl. So if it's your first time, welcome to what we're doing. Here we're just these office hours and basically streaming in general. Where we're hoping to cultivate more blockchain education, be transparent about the work we're doing at Topl and how we're trying to topple the world. Hashtag topple the world, I guess. And just bring um, you know a robust mindset to how we develop and how we actually try to um, specify and communicate our ideas across the entire community and broader crypto ecosystem. So to that end, what I want to talk about today and spend a little bit of time, and hopefully we can get some questions and see where we go from that. I'm trying to make sure I can keep an eye on chat. But what I want to do today is go through how we're going to do keys, or how we're going to do mnemonics in within Topl, in the Tetra version of Topl. So Tetra, again, in case you're unaware, is going to be the next generation of the Topl protocol. We currently we are in the Dion era of the network. That's where we have a public mainnet and testnet available right now. As well as a few SDK libraries like Bramble.js and Bramble.sc. But the utility of the Dion network is, going to be upgraded in Tetra to allow much more flexibility and much more rigor in actually the definition of the protocol. So to that end, we have a repo that I want to go over with folks. And I think it is not this screen. Sorry. Wait, why is it still on that screen? When I do this, oh, dang it. Why is it not? Oh, sorry, everyone. I thought it would. Why? Nothing ever works the way it needs to work. I know how to do this. Sorry, everyone. The Mac is not treating me well right now. So I apologize for the technical difficulties. So what I want to show is a repository that we have under GitHub called Reference Crypto. Reference Crypto is it's a work in progress repository to allow us to specify and have a single home for where the specification of the protocol is living. Again, it is, like I said, it's a work in progress, so it's a bit of a living document at the moment. It more than likely is going to turn into our SDK definition, right? Just a singular protocol definition for not only what happens on chain and how transactions and all the ledger definitions and things happen, but specifically how to interact with those ledger definitions and how to actually get transactions on chain. So when I say SDK, there will be a separate definition for that kind of encompasses some of the things that we're doing today. Okay, so why am I doing that? That's not actually what I meant to do. We're gonna do this. We're gonna try this, and we're gonna go here. Oh, look at that. Okay, so once more, forgive me for a little bit of technical difficulties there, please. But here we go. So this is our reference crypto repository. Let's go into that view. Like I said, it is a bit of a work in progress at the moment. We have some older things, some manuscripts that we've been working on that were in there that are going to migrate. But the things we're going to focus on today are under specs. And then we have some specifications for signing routines that are in here. But what I want to cover today is our specifications for key generation and how we're going to do specifically root key generation and child key derivation. so we'll just kind of walk through this and see what we have. And if anyone has any questions along the way, please feel free to post them in chat, and I'll be happy to elaborate. So first off, let's see. I think this is probably big enough for everyone. It looks big enough on my screen. All right. So yeah, this is talking about all the keys. I have outlined all the keys for what's in the underneath signing, which is let's see. Where can I do this quickly? Where do you have a good list really quickly? I'm thinking. Yeah, let's just go look in their signing really quick. That's the easiest place to enumerate them. So we have the names that we give to them are curve 25519 axolotl. This is a signing routine that was developed by Whisper Systems, and it's a legacy scheme. We are currently in the deprecation phase of moving away from these sorts of signing keys. But this is the primary key used in the Dion era of the network. I am showing the reference crypto repository. So under github.com, I'm sorry. So there's a question in the chat. I apologize about that. So just, yeah. Which repo? And the repo is, maybe I should have made a little thing, but we're looking at https:// yeah, there you go. Thank you. That's where we're at right now. So thank you for that, Imgrand. So the digital signatures. So yeah, this is the curve 25519 is our older one that we're deprecating. The ed 25519 is the single signature scheme. So it's the underlying signature scheme, but ed 25519 is just the label we give to the single key scheme, right? Extended ed 25519 is the name we give, is the label we assign to the signing scheme, which allows for child keys to be derived. So ed 25519 is a normal RFC 8032 compliant secret key, and with a verification key that generates I'm sorry, that's where the RFC, that 8032 signature compliance comes in, is how you specify the signatures. But yeah, so that's just a normal key pair. Whereas the extended ed 25519 uses a process, uses a scheme developed by, I apologize. Yeah, it's in here, but I don't remember the group. But it is this BIP32 ed 25519 scheme, and I feel like it starts with an N. Oh, Evernym, that's the group. So yeah, so this is the modification to the ed 25519 keys in order to allow for linearity in the key space, so that you can do the normal coupling schemes that are required for child key derivation processes. And these child key derivation, and so we'll get to that in a second. So that's just what the extended one is, and then we have a couple of KES ones in here. I'm not going to spend too much time, but I just want to say the KES and the VRF, these last three, are specific to consensus, the cryptography we use in the consensus protocol. If you're interested in the KES, it's based off the MMM construction, and that's actually what's in this up at the top. There's a really nice little set theory formal specification or set theoretic protocol boxes of going over introducing the MMM scheme and talking about our construction. So if you have any comments or if anyone's interested, please come take a look. Let us know. There is some more under there. There's also some reference implementations and test vectors as well. And the last one is that VRF, and the VRF is specific to it is a. I know I kind of went into a little bit of signing stuff and all the keys, but there's this EC VRF specification that's currently a request for comment, if I believe, or an informational draft. So this is the spec that we're compatible with. Is this IRTF? Okay. So those are all the schemes, or all the signing routines that we specify or we label. And so then each one of them underneath generation, how do we actually generate the keys, or how do we integrate the generation process for each? I'm sorry. How do we integrate a single generation process into each one of those keys? Because that was the goal. And so we had a standard process across all of Tetra signing routines for how to generate these keys. So that process is in the generation part, and I'll say that the root key generation is partially compatible with BIP 39, right? So we do support mnemonics. Topl does support having or importing 12 or 15 or 18 or 21 or 24 word mnemonics that conform to the BIP 39 word lists. However, BIP 39, like as I state right here, when I say partially compatible, what I mean is that we're compatible with the generating the mnemonic and word list sections. We are not compatible with the mnemonic from seed section. This mnemonic from seed section is not what is outlined in this process. BIP 39 is not described by this diagram. So I just want to point out that this is why so specifically it's very, very important to understand that we have partial compatibility with BIP 39 in primarily because if you create the seed the way BIP 39 says, you won't get the same keys that using a mnemonic. We adopted our process from this another process called SLIP 23. Unfortunately, there, as seems to be the case in many in emerging. Oh my goodness, what just happened? I didn't mean to do that. I apologize, everyone. These emerging technologies, right? When you're on the cutting edge, things it's hard to. People are just making stuff all the time, and so its documentation goes stale quickly, or it may not have never ever even existed. So, right. So this is just one of those. This is why we're trying to make an effort to have a place where we make sure everything that we need to define for the wider community is available. This SLIP 23 though is from Satoshi Labs, Treasure, and they had made this when they were trying to integrate with, as far as I understand, when they were trying to integrate with some Cardano wallets, and Cardano had this older implementation for the Byron era, and then they developed this newer Icarus implementation. The reason we adopted I'm saying we are, because this is a very kind of obscure slip. I'm trying to minimize the number of different schemes that exist overall. But even though I'm kind of adding our own, because I say again, we're not, while we adopted this process, we don't for how we generate root keys in Topl or in the Tetra era, we do not always do step 5, right? Because this process is specific for, or was specifically specified for generating the root key of an extended ed 25519 child key derivation scheme, or HD scheme. So I just want to point out that's kind of other things. Some it's okay. For root key generation, we can leave it at that. In general, the process is going to always. This is the process that we follow, and all of our schemes follow this. The curve 25519 scheme, the ed 25519, the extended ed 25519, all the single key schemes and the HD schemes all use the same process, right? And in this process, you can I should add a legend to it. But the blue squares can be thought of as like data objects or data, or pieces of data, and the yellow boxes are the functions, or they're, you feed in the data, you feed in this thing, and you should get an output. So the first step to go from here's roughly an outline of the process we're taking, and like I said, you can tell it's pretty closely related to it looks very similar to what we just saw in SLIP 23. But the first thing we do, and why 0 is here is say, we're just going to define that M is a BIP39 mnemonic. So we just have a 12, 15, 18 word mnemonic, something like that. And P is a passphrase. It's just a string passphrase. So we're just going to say, those two things. So this mnemonic M is this blue thing, and this passphrase that I'm saying is this little one right here. Okay, so those are our two inputs to need to get a secret key. We need a mnemonic and a passphrase. So from the mnemonic, we will then go through the BIP39 process, which is specified if you kind of reverse engineer this paragraph and how they say to generate. So given some entropy, how you go back and how you pick your word list. If you flip that around and you go from, okay, if I have a word list, how do I get some entropy? You can define how to do it. So that's the first step, is you regain your entropy from the mnemonic. The second step is we do this slip23 Icarus part, which is really just compute you put that entropy, or what we call it entropy, into a PBKDF2 key derivation function, and using with a 4,096 iterations and a decay length of 96, and then this P passphrase, this thing that you assign to P, is what you put in for the first argument, and the first argument in this function is typically called password. So I know it's a little confusing, but you're just putting P as the first argument. And then salt is going to be a thing that it's part of the algorithm. You define this, you pick a new salt. I apologize. I apologize. No, ignore the last thing. I apologize. Sorry. E is the entropy that you got from the step before. Yeah, my mistake. I just misspoke. So M goes to E. E is the thing you put in for this argument that's called salt. P is the thing you put in for this argument that's called password. And then these two are fixed. So at the output of this, you have a seed, or something we just call a seed, right? These are all just labels that were science stuff. And then you feed the seed into something I call a seed specific or a routine specific signing routine. Primarily, this was introduced to allow for the clamping that has to happen in certain protocols, right? Like I mentioned earlier, you have to modify the original key space of the ED 25519 scheme to only have keys that are linear, and that's done through this last little, or this third little box here. This signing the routine specific steps. Sometimes it's just identity though. Like in normal ED 25519 keys, any 32 byte number is a valid key, so you just pick it. You could just pick one, at least a valid private key, right? So sometimes that yellow box, that sign specific thing, or I'm sorry, routine specific thing, is just identity. You just pass it through, but sometimes it's not. All right. So then we go a little further to just be super pedantic about it, and I name each one of these things, and we give test vectors. Let's see where we're at. We're at 320. Okay, good. So the first step, obviously, really, dang, I can't think of the word right now. Anyway, the first step, we're just gonna, we're going from mnemonic to entropy. So, very interestingly named. It's just mnemonic to entropy. The second one is entropy to seed, and the third one is seed to secret key, right? So each one of these, we can go and say, okay, well, how do you do? What is your specification for mnemonic to entropy? Well, like I said, we're compatible with this. This is really what we how we do it, and then we give a bunch of test vectors. I went around and I guess I didn't do it here, but we did pull a lot of these test vectors. I tried to go as far across different repos and different places I could find using Google, the magic of Google. But if anyone does know of more or better specifications, or really even just as a comment on any of this work, I'd really love to know if is everything we're doing like good? Is it good? Is it bad? Is it something that shouldn't be done? Maybe that's what I need to say, is tell me all the bad things I've been doing, and that might motivate people to actually look for bad things. But so the second part is how we do the seed generation. And the seed, like I said, is just this pbkdf function. This is a pretty common thing. Literally, this is just a call to an inbuilt function, right? Like, I don't know. I'm just showing the. I know this is a little like pedantic because it doesn't. This isn't actually really a useful. It's just a. Oh my goodness! I don't know if that was. Whew. All right. The real reason this is here is so I can have to specify these guys. I can say what the given the this entropy and this password, here's what the seed should be. Lastly, we have seed to secret key. So this is where I go and I specify each one of those like routine specific things. Again, it is given in Scala syntax, but these should be generic for any routine, which is why we give the test vectors for all the different ones. I guess in some, even though, yeah, this is just slicing. So here, the 32, even though it's 32 bytes, I'm sorry, the output of the seed of the key derivation function is 96 bytes. So here we're just slicing. So when I said earlier identity, that's, I did kind of misspeak. This is essentially identity, but I'm slicing. So technically it's not, I guess. Yeah. And then but this was the real reason, like, some of these routines have these weird clamping things that you have to do where not all keys are valid keys. Sorry, I saw the flash of light outside. I was trying not to jump again. Okay, so that is that. At least those guys. I don't give separate test vectors for the seed to secret key. Primarily because I feel like it's a little redundant. They're really obvious what you should be doing. Like they're just bit flipping usually, and it's fully specified by the like kind of end to end or maybe not end to end but integration test vectors, where you go from a mnemonic and a password. Remember, those are the two things I said you needed, right? You need a mnemonic and a password or a passphrase. And then you should be able to get the secret keys, right? So this fully specifies given a mnemonic, going through the mnemonic to entropy, entropy to secret key to, entropy to seed to secret key. And then this is the output secret key. All right. And that is generation. That is half of the problem. The next step that we want to think about would be child key derivation, which is probably much more like familiar process for people because we tend to talk about that a lot more in the context of blockchain systems. But before I go into that, I guess I'll pause and see if there are any questions or anything that maybe people didn't understand or would like clarity on. Get a drink of water. Oh, okay. Okay. All right. Well, I guess if there are any questions, please feel free to put them in the chat whenever you'd like. Okay, so moving on to the child key derivation. We again, I want to be very clear that we are not compatible with BIP32 or BIP44, right? And that is primarily because BIP32 is specified for here we go. We'll assume the public cryptography used in Cryptoin in Bitcoin, namely the ECC cryptography using the field and curve parameters defined by SECP 256K1. Because of that sentence right there, we can never be we cannot even be partially compatible. We could be compatible if we adopted SECP 256K1, but we do not use that. We use this BIP32 at 25519, which uses the underlying elliptic curve of the 25519 elliptic curve. which is just a very efficient curve for it's a curve that allows for the creation of efficient the efficient creation of signatures, I guess is the thing I should say. That's what I'm trying to say. The efficient creation of strong signatures, which is the strong part is important for the underlying cryptography. But okay, so that's why we're not 32 compatible. And then because 44, we're not 44 compatible because we're going to expand the scheme here, the lower three keys. We also don't use a purpose of 44. I did not put a reference to I should have. That's really silly. So you'll notice that so if we're not SECP2, if we don't use SECP256K1, so we can't be BIP32 compatible. What are we? And so we use, for purpose, we use the field 1852, since we also fall under, like Cardano uses the same thing. And they just define that if you're actually using BIP32 at 25519, then they propose using purpose of 1852 instead of 44. So we adopt this. So that means that we are not 44 compatible. And then, yeah. So I will say these last three, how we actually use these last two schemes, this derivation or this specification at the moment only really concerns what we just covered was how we get the M. That's the root key. And then we've only really settled on these first two, right? The purpose and the coin type of the chain. We are still in active discussion on how best to organize these three. So stay tuned. Just like in the previous schemes, we do use the BIP32, or that's the whole point of BIP32 at 25519, is to be able to use the same scheme, the underlying derivation scheme, to enable HD wallets, but over a different curve, right? So using a different signing routine. So, like I said, the purpose is set to 1852 following SIP 1852. I guess I did link it. That's good. Since we follow the BIP32 at 25519 algorithm, I will say for maybe anyone in the future watching this, supposedly Polkadot had a link in their documentation that got removed, saying that BIP32 at 25519 had a vulnerability if the implementer allowed for an unbounded depth in the path. However, the
All right, who wants to hear a funny joke? Because I mean, I do too. Does anyone have a funny joke? I really need a funny joke right about now. Yeah, I think I definitely think that the thunderstorms probably didn't get him, but they did probably get his internet service provider or power company, or both. That would be a real doozy. So yeah, arbitrary depth on extended ed 25519 keys. I don't know what the rest of his sentence was going to be, but I'm pretty sure in our Scala implementation we like it's just like a structural depth. It's not really just an arbitrary tree type depth thing. So that's kind of my comment there. This is phenomenal. This is exactly what I was hoping for. Two peanuts walked into a bar and one was assaulted. That's amazing. Thank you. Thank you so much. That makes me happy. Thank you, YouTube chat. Luckily, I think the power's back and the internet's back. Welcome back, James.
Power seems to be back.
We were doing stand-up comedy where the crowd told the jokes for me. I loved it.
Oh, that's pretty good. Well, yeah, thank you for jumping in there. The storms, I don't know, it didn't sound so bad, but every now and then just, I guess we really need it though. So, alrighty.
Arbitrary depth extended at 25519 keys. Why are we good?
Yeah. Okay. Yeah. So the arbitrary depth, like I said, I'm very curious if anyone has any information. I'm going to just throw this out and I'm going to try and manifest it into existence. I really want to know what this vulnerability was because there was a link in on some old Polkadot documentation and a few other places on the internet that link to this old W3 forums post, but the post had gotten taken down by the time I was researching this, so I never got to read the vulnerability or potential vulnerability. Maybe it's not even vulnerability. Maybe it got resolved, and that's why I can't find it. So literally, if anyone else has any information about that, one that's hilarious. I missed the joke. I like it. Yeah. So at least we know that vulnerability might exist. So we're not going to allow for unbounded path usage. But like I said, I'm going to just throw it out there if anyone wants to let us know. Let's see. So then under coin type, Topl uses 7091 and has registered this with the slip44 repo, even though I know slip44 repo is specifically for groups using BIP44, but there's a seeming lack of shelling points around which to coordinate across the wider community, across the wider crypto space. So lacking those sorts of things, I'm going to make my own and try and use the slip44 repository. So as I said, the further derivation of the last three indices are relegated to a future tip, more than likely, as it'll probably be a community standard or a set of community standards on how to actually most effectively take advantage of these three levels. Again, just for the sake of rigor, trying we provide the test vectors for a given root secret key. Sometimes we give a root verification key, and we specify the child secret key and the child verification key following this path, right? So given a root secret key, you can then derive child secret keys. Given a root verification key and a particular type of path, that is what the soft indices are. If anyone's unaware, that is the difference between a soft and a hardened indice. Is that soft indices? So if you don't have an apostrophe on your path when you apply an index, it means that you can take a root verification key and go down to a child verification key. But if you use a hardened index, you cannot go from a root verification key directly to a child verification key. you can only go from a root secret key to a child secret key and then to the child verification key, right? So hardened indices mean that you can only derive child secret keys. Soft indices mean that you can derive child secret keys and child verification keys. Just throwing that out there because it took me a little while to understand that at first. So yeah, so in the cases where we provide just soft, then I give a child verification key and ensure that in the inputs and in the inputs and ensure that we get that on the output. But in cases where we provide a hard derivation path, I just give the root secret key, and then you have to go through the child secret key, and I also just check the child verification key by specifying it and then coming through the child secret key. So anyway, a little bit of how to read that. And yeah, actually that might be kind of, that's most of it, I think. Let's see. We can maybe go through like the last little bit would be going through like what is a mnemonic? How does Topl represent mnemonics? Again, this is in like a bit of Scala syntax. Hopefully it's not, I'm not trying to do a bunch of function definitions. I'm really just trying to write object code or class type code in Scala syntax. So like I said, hopefully it's readable. I don't think it's too bad. But fundamentally the term the term mnemonic is, I guess in my opinion, a little overloaded. Like people say mnemonic and they mean a bunch of things. So I try to refer to internally, I just have a class called a phrase, and that is my so mnemonic can be any number of things. A mnemonic could be a phrase, or mnemonic could be just the string, right? But a phrase is specifically an index of strings that are fixed to one of these lengths and conforms to is only composed of words out of this word list, which is represented again by another just sequence of words. So that's like what the phrase is, or AKA the mnemonic. So this phrase is what I turn into a entropy, or the mnemonic in entropy, mnemonic to entropy. That's the first step. And then entropy is really just, it's just a wrapper. Entropy is just bytes. It's nothing special. It is a fixed value. It does have to conform to to what we saw before in, I know I don't like it when I do this, have to do this stuff. But what I mean to do, I meant to go here. Did I not? Oh, I'm sorry. Oh, I think I meant to go to this one. Yeah, it does conform. So entropy has to conform to this table, right? So just like mnemonic lengths can only be 12 or 15, the number of words is 12 or 15 or 18 or 21 or 24. The size of the entropy is then correspondingly 128, 160, 192, 224, 256 bits. And that means that the checksum is then 4, 5, 6, 7, 8. And then the entire size, the bit size of your mnemonic, which is represented by these 12 words. So for a 12-word mnemonic, it's 132 bits of data, right? Or for a 24-word mnemonic, that's 264 bits of data, right? Encoded in those 24 words. So when I say the entropy is just, it's just I have it defined as just like a wrapper around bytes. This is honestly a pretty like somewhat meaningless statement. I really only put it here so I don't know. It's honestly, it's a little more confusing to me now that I have it here and I'm coming back to it. But it can only be 16, 20, up to 32, right? The seed is again, well, the seed is also a byte array, but it's fixed at 96, right? Because 96 is the longest we need, so we pull out. Yes, 8 bits is 1 byte. Yeah. and then our then this is just the definition for secret keys. The So you can see like I took the names. The curve 25519 is really just a wrapper around 32 bytes of data, and a ed 25519 is again just a wrapper around 32 bytes of data, but they aren't necessarily interchangeable with one another. So that's why we introduced this wrapper around it. So then extended is just 96 bytes. The VRF secret key is 32 bytes, and then the two KES product, the KES sum and product are their secret keys are kind of complicated, primarily because we're trying to minimize the number of different ways that we use sign routines, and so we kind of made this. I mean, ultimately, we're really just if you dig into how these things are constructed, these 32 bytes can actually mean it's like a concatenation of multiple things. So we're really just kind of exposing some higher level stuff that's internal to the protocol at maybe a level at a bit of a higher level. But yeah, anyway, this is the definition of those. Okay, I mean that's basically all of our how we do HD keys. That's pretty much all of it. The big thing that we're working on now to improve upon this is we have all of this done in the Scala code base at the moment, but we would like to expand it to have reference implementations in Python so that we can minimize the or in Python we can take like really simple implementations or like naive implementations of the like elliptic curve cryptography and boil down and just have like very simple reference implementations for passing the test vectors and having things that are available for saying like this is we're able to reproduce this behavior across multiple languages and try to ferret out if we've underspecified anything by only having it in JavaScript and Scala at the moment. Some of it in JavaScript, not all. It's not. We don't have all of the specifications done in JavaScript, only some of them. So yeah, that's where we're kind of at in terms of further specifying, as well as building out the last three fields of the keys. I've tried to stay somewhat in the bounds of where I've seen other groups, in particular, like since we are following at 2519 because we needed a strong signature scheme. It seems that there's only a few groups that I can find that have fairly extensive documentation on using at 2519. So I'm a bit relegated to doing that in terms of the point I'm trying to make is for building compatibility with particularly hardware wallets. Right, we would like to target support for, or I would like to target support for hardware wallets at some point, or like to provide support for hardware wallets at some point. So I can't commit to that being on the roadmap or anything that we could necessarily get done, in short order. But it definitely would be something that I don't want to close off a route to. So therein lies the point or the motivation for trying to maintain compatibility with known standards instead of trying to strike out on our own, or really, as much compatibility as we can provide to known standards or already defined standards. All right. Well, I know I guess I'm ending a little bit early, but I guess I will ask one more time if anyone has any questions or let's see. I will say if you're, we do have another live stream that's going to come on after this. Sean, I don't know if Sean mentioned that a second ago, but he's going to be going over some of the networking improvements that we made in the Tetra protocol, specifically around how we the communication protocols, like the actual the protocol that the two peers will execute when they're performing the data exchange in the network or in Tetra. So I would, if you're interested, stick around. If you have if anything came up or if someone not right now or watching this later has a question around keys, please feel free to reach out. Hopefully we won't have to modify, or we won't change anything so fast that this gets outdated. But yeah, I guess I'm gonna ask the wizards to maybe help me close this out. I know I need the closing banner, and then I'll do that shout out, and then we can wrap it up. Awesome. So yeah, so appreciate it. Thanks for watching. If you have any questions or want to interact with us, you can find us on Twitter or LinkedIn, GitHub, or Twitch. And we are also available on Discord, so come hang out. We have a nice little community going on there. And yeah, we'd love to see you. So awesome. Well, Johnny, I really appreciate you hanging out with us. So yeah. Well, thanks everyone. I hope you have a good afternoon, good evening, good morning, day, night, wherever you may be. And we will talk to you next time. Bye, everyone.